we are learning about cutset of a graph. In my last video, I have proved one property of a cutset, that is, every cutset in a connected graph G must contain at least one branch of every spanning tree. Now, will the converse also be true? I mean to say, will any minimal set of edges containing at least one branch of every spanning tree be a cut set? Answer says yes. Let us see how it is. I'm taking a connected graph G and I'm taking any minimal set of edges which has got at least one branch of every spanning tree. Now, will that set is a cut set or not? Answer says it is a cut set. Let us prove how it is. Okay. I'm taking a connected graph G. Let G be a connected graph. Okay. And let Q be a minimal set of edges. Minimal set of edges containing at least one branch of every spanning tree. Containing at least one branch of every spanning tree. Okay. I'm taking a minimal set as Q. Now, I'm considering the graph G minus Q. How it is? It's a subgraph that is obtained by removing the edges of Q from G. So, now this subgraph G minus Q contains no spanning trees. This G minus Q is obtained by removing the edges of Q. Okay. So, this subgraph has no spanning tree of G, of course, because I have removed the edges of Q, so it has no spanning tree of graph G. Okay. Now it implies that G minus Q is disconnected. In fact, it will have one component which just has an isolated vertex. I'll prove this by giving example also. This is a theoretical example. Okay, I'm taking set Q, which is a minimal set of edges which has got at least one branch of every spanning tree. I'm considering G minus Q. I can observe that it has no spanning tree of G and this is a disconnected subgraph. G minus Q is disconnected. In fact, it has got one such component which has got only one isolated vertex. Also, see what I have taken, since Q is a minimal set of edges with this property. Q is the minimal set of edges which has got one branch of every spanning tree. So, any edge E from Q, if I take any edge E from Q, okay, if I take any edge E from Q, if it is returned to G minus Q, is returned to G minus Q, will create at least one spanning tree. If I take any one edge from Q, since it's a minimal set, I'm considering one edge E from Q and I'm adding to G minus Q. Return to G minus Q will be, will create at least one spanning tree. Thus, what happens? G minus Q plus with the edge E will be a connected graph. is a connected graph. Since I have mentioned that it will have one spanning tree, at least one spanning tree, so it will be a connected graph. Therefore, Q is a minimal set of edges. Q is a minimal set of edges whose removal from G will disconnect G. This is nothing but the definition of cut set. Therefore, Q is a minimal set of edges whose removal from G disconnects G. This is by definition, it's a cut set. Thus, by definition, is a cut set. Hence the proof. That's what I have to prove. I have taken a minimal set of edges which has got at least one branch of spanning tree. I have to prove this minimal set is a cut set. Okay. Now I have taken Q as a minimal set of edges which has got one branch of every spanning tree, and I am taking G minus Q. I can observe that it has got no spanning tree of G. In fact, G minus Q is a disconnected graph. So I am taking any edge from Q, that is E. I am returning it to G minus Q. I am adding that edge to G minus Q, so that G minus Q plus E will be a connected graph. Therefore, I can say Q is a minimal set of edges whose removal from G will disconnect G. Therefore, by the definition of cut set, this Q is nothing but a cut set. Say, for example, if I take a simple graph like this, with edges say A, B, C, D and E. I'll define a spanning tree. Let it be like this. A, D and C is my spanning tree, say T. This is my graph G. Okay. I'll take a minimal set of edges which has got one branch of every spanning tree. Let me take it as say A comma B. Now what happens to G minus Q? You can guess. G minus Q. Okay. This is G. I am removing H, A and B. A and B. See, I have got one edge of spanning tree, one branch of spanning tree. Okay, so G minus Q looks like this. D, C and E. I mentioned no, in fact it is a disconnected graph. G minus Q is a disconnected graph in which one vertex, one component has only an isolated vertex. So it looks like this now, G minus Q. If I take any edge, say E, that edge is B here. If I add that edge to G minus Q plus B, it looks like this. Adding an edge D, C, E. Now you can observe that it is a connected graph. Okay, that's what the thing is. If I take any minimal set of edges, it will be a cut set. That is, every circuit have even number of edges in common with any cut set. If I have a cut set and cut set of a graph and I'm taking a cycle of a graph, then they share even number of edges. So let us take S as a cut set of a graph G. S be a cut set of graph G or cut set in graph G. And if I remove this S from my graph G is my graph. If I remove S from G, then it will be a disconnected graph, and vertices of G are giving me vertices of G are distributed to two set of vertices, say V1 and V2. Let the removal of S partition the vertices of G, means G minus S will partition the vertices of G into two subsets. In fact, they are disjoint into two disjoint subsets. Say I'm calling them as V1 and V2. Okay, two subsets of vertices. Say G is my graph, which has got, suppose which has V vertex set as V, and I'm taking a cut set of G, that is S. If I remove S from G, then the graph will be disconnected and vertex set is distributed into two sets. Say let us take it as V1 and V2. Now say I can draw simple graph. Suppose I'm just drawing G minus S. It's a general graph. Okay, they have got these kind structures, sort of some edges were already there. Okay, something like this. This is giving me vertex set V1 and V2. This is after I'm taking the partition after removing S from G. So my vertex set is partitioned to two set. This is one set, that is V1, and this is another set, V2. Okay, now what I'm doing is I'm going to draw a circuit in G. Okay, say let me take gamma as a circuit. Let gamma be a circuit or cycle in G. How is this? If all the vertices of this gamma are in the vertex set V1, entirely in V1 or in V2, then number of edges in common with S, cut set S and gamma is 0. There are no edges in common, right? Say if my entire circuit, I'm considering generally a circuit, okay? If that circuit is entirely in the vertex set V1, suppose this is my circuit, suppose, okay? If that is the case, then the number of edges in common with this cut set and gamma is 0, which is an even number. Similarly, if the circuit is entirely in the vertex set V2, then this partition, number of edges in common with S and gamma is 0. That's all. If all the vertices of gamma are entirely within V1 or V2, then the number of edges in common, or edges in common with S and gamma is 0. That is, I can say number of edges in common with S and gamma is 0, which is an even number in fact. I have a cut set, yes, and which is making a partition like this for a graph G. Okay, a vertex set is V1 and vertex set V2. These two are the subsets of vertices of G by the cut set S. Now I am taking a circuit gamma in G. It may have all the vertices in vertex set V1 or in V2. Okay, if they have entirely all the vertices entirely in V1, then the number of edges in common with the cut set and V1 is 0. Similarly, if entirely that circuit is in V2, then number of edges in common with S and V2 is 0. S and gamma is 0. Therefore, number of edges in S intersection gamma is 0 if gamma is entirely in V1 or in V2, which gives me an even number. Now the situation is different. If the circuit gamma has the edges whose end vertices are in V1 or in V2, both some end vertices are in V1 and some are in V2, then what happens? So on the other hand, if some vertices of gamma are in V1 and some in V2, then how can I draw circuit? How the circuit will be? Some end vertices of the edges of gamma are in V1 and some in V2. Suppose if I start from this, okay, I want to have a circuit whose some vertices are in V1, some are in V2. So if I go by this, I'm going this way, I'll take up this edge, take up this edge, then I'll come back. I have to have the circuit, so by that nature I have to come back somewhere here. If I come, then I'll form one circuit, or if I go like this and I'll come back to this, like that. Every time if I go, then I should come back, like that. So if some vertices of gamma are in V1 and some are in V2, then we traverse back and forth between the vertex sets V1 and V2 as we traverse a circuit, right? Every time if I go, then I have to come back. If I go like this, then I have to come back. So by the closed nature of the circuit, number of edges we traverse between V1 and V2 is even. Every time if I go like this, then I should come back to have a circuit. So this is just because of the closed nature of a circuit. Number of edges we traverse between V1 and V2 is even. It must be even. And we know that every edge in S has one end vertex. Every edge in S has one end vertex in V1 and other in V2, since S is a cut set. So no other edge in G has this property. Therefore, number of edges in common with the cut set and a cycle is even. So I have written, if some vertices of gamma are in V1 and some are in V2, then we traverse back and forth between the sets V1 and V2 as we traverse a circuit, right? As we traverse circuit or cycle. And of course, because of the closed nature, of a circuit, number of edges we traverse between V1 and V2. It must be an even number. It must be even. I hope you got the point. Every time to draw a circuit, and if I start from this vertex from a set V1, if I go like this, then to form a circuit I have to come back. So every time I'm moving back and forth, okay, to form a circuit. So every time I'm traveling twice, once like this and I'm coming back. So this is an even number every time. So even number of times I'm moving from V1 to V2 or V2 to V1. So number of edges in common with this circuit and a cut set is even. It's just because every edge in S has one end vertex in V1 and another in V2. So I'll continue writing. Since every edge in S has one end vertex in V1 and the other in V2, and no edge in G has this property other than the edges of S, and no other edge in G has this property Therefore, the number of edges common to S and gamma is even. Therefore, number of edges common to S and gamma is